So when we looked at different kinds of bonding, one of the things that we said that atoms can do to become more stable is they can share their electrons. This happens when two elements that are reacting together, and it can be more than two elements, but for us, we're going to keep it simple and just stick with two elements. If two elements that are reacting have nearly completed valence shells, so those are the nonmetals, right? The halogens, which have 7 electrons in their valence shell, or the oxygen group, which has 6, or the nitrogen group, which has 5, or even the carbon group that we've kind of ignored to this point with 4. All of those things want to fill up their valence shell by gaining electrons. But if they are reacting with something else that is wanting to gain electrons, their only option then really is to share their electrons. By sharing the electrons between them, it's as if each one of them has completed their valence shell. That is called a covalent bond. So we're going to focus right now on covalent bonding. Okay, so in a covalent bond, what we have is a shared pair of electrons. Electrons are being shared between atoms. They're called covalent because the prefix co means partner. Valent, of course, from valence electrons. So they are partnering to fill their valence shells. These bonds, as I mentioned already, are going to form between the nonmetals because the nonmetals have a nearly filled valence shell. Neither of the atoms that are involved is wanting to give away their electrons. They only want to gain. So by sharing, neither has to. They don't have to give away their electrons. They can instead allow their electrons to be shared between the nucleus of both atoms. And there's that attraction because remember that the nucleus has protons in it and has a positive charge. So these shared electrons then are actually attracted to both nuclei. When you represent this, the simplest way actually to represent it, instead of using a drawing, is to just show it with a line between the two letters. So for example, when two iodine atoms share a pair of valence electrons, giving each one the 8 valence electrons they're looking for, we can write it as I with a dash or a line, and then another I. Every one of those little dashes or lines represents a pair of shared electrons, or a covalent bond. How many covalent bonds an atom can form really depends on how many electrons it's needing to fill its valence shell. So group 17 actually, that we've already looked at with iodine, forms a single covalent bond because they really only need to gain one electron. So by sharing one electron with another atom, they have completed their valence shell. They have gone from 7 valence electrons to 8. Group 16 has 6 valence electrons already, so in needing to fill that with 2 more, forms 2 covalent bonds. Group 15, with their 5 valence electrons, actually forms 3 covalent bonds because they're needing to gain those 3 extra electrons. They're doing that by sharing, but it is 3 bonds required to make that happen. And then group 14, that we've kind of ignored to this point, carbon's group, they have only 4 valence electrons. If they use their 4 electrons and share with other atoms, they will form 4 covalent bonds in order to complete their valence shell. So covalent bonds are always formed by sharing valence electrons, which means they actually exist as little bitty molecules, individual molecules. The way that the atoms interact with each other and bond together in sharing their electrons, gives each one of these compounds a unique three-dimensional shape. So how these atoms interact gives it an overall shape for its molecule. The molecular shape can also affect what kind of properties these compounds have. Because most of these compounds end up with evenly shared electrons that are moving between the two atoms or three atoms and so on, they exist as independent molecules that are not attracted to each other. And for that reason, there's really very little attraction between molecules. And that will mean that it doesn't take very much energy to break them apart. That gives them a low melting point and a low boiling point. It really takes a lot less energy to break up these atoms because they really are individual molecules. So covalent bonds tend to be kind of weaker bonds that are fairly easy to break. And so we have compounds then that are frequently gases at room temperature, or solids that have, or liquids for that matter, I'm sorry, but or solids that have very low melting points. There are no charges involved, so that means they are not conductors of electricity in any way. But when atoms share their electrons, sometimes they don't share very equally. I always think of this kind of like the difference between friends sharing a package of Oreos and brothers and sisters sharing a package of Oreos, right? If the Oreos are the electrons, how evenly are they shared? Well, if you share with your friends, you probably share them pretty evenly. So when atoms are sharing these electrons, and they share them very equally, meaning the electrons spend equal amounts of time between both atoms, then the bonds that are formed are called nonpolar bonds. This happens especially in atoms of the same element. When they bond in pairs, they both pull equally on those shared electrons because they have a nucleus of exactly the same size, providing the exact same amount of pull. So an example of a nonpolar covalent bond is a diatomic, a two-atom molecule. There are 7 diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are all diatomics. That means that they exist as 2-atom molecules. That's where the diatomic comes from. Di meaning 2, atomic meaning atoms. 2-atom molecules. They exist this way in nature. By sharing their valence electrons, they are slightly more stable than they are as individual atoms. And so they form covalent bonds. But because those electrons are shared very evenly, they are called nonpolar covalent bonds. So you can see here a diagram that includes the 7 diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. But what happens if they don't share evenly? That I had a mistake in my slideshow. It's fixed now. So what happens when atoms don't share their electrons equally is that these electrons are actually pulled by one atom a little harder than they are pulled by the other atom. That causes those electrons then to spend more time on one side of the molecule than they do on the other. They're pulled more closely to the atom that is stronger. And by spending more time there, it actually gives that side of the molecule a slight negative charge and leaves the other side of the molecule as if it is almost missing its electrons. And so it gives that side of the molecule a slight positive charge. When that happens, we call it a polar bond. It has formed poles, like the North and South Pole. So that's why it's called a polar bond. We can use little symbols called delta symbols, the Greek letter delta. And if the side of the molecule has the slight positive charge, we use delta plus or delta positive, and the side that is slightly negative, we use delta negative. The delta symbol represents partial, so it's showing that it only has the partial charge. It's not completely formed an ion. So water is like this. Oxygen up here is much, much bigger and stronger than hydrogen atoms are. So oxygen pulls very, very hard on the electrons that it is sharing with the two hydrogen atoms. The electrons then spend more time next to the oxygen atom, making it as if it were slightly negative. So we put this delta negative sign on the oxygen side of the molecule. Each of the hydrogen atoms then, it's almost as if they have lost their electron and have become slightly positive. So each of the hydrogen atoms then has a slight positive charge, and we use that delta positive to represent it. So anytime that electrons are not shared equally between the atoms in a molecule, the molecule is called a polar molecule.